If you plug in 1 or something like that, or -1, you get sine of pi. That's sine of pi. We all know that. Of course, that's 0. So you get 0, 0. Let me change colors so we can see it. So this function, it does sort of something like this, and then it starts doing its little trick thing, and it does something like this. Starts doing its trick thing. But this is where I'm not going to do justice. Go look at your calculator. If you want to break your calculator, you want to make it mad, plug this function in and zoom in on 0. Go to Desmos and go look at that thing. It is, you'll see like this rectangle, this block. What's happening is the function is going bananas as you get closer to 0. It goes up and down and up and down and up and down. In fact, it oscillates infinitely many times. It just doesn't like you dividing by 0 here. It's really angry. And calculators have a hard time capturing this. So it oscillates between 1 and -1 infinitely many times. Right? The sign graph is down above and down below. So this function goes crazy. It doesn't have a good behavior. So now how do you say, so you say, okay, well, I can't plug in. So you say like f of 0, which is, this is undefined. You can't divide by 0. So, here come limits. Can I tell what the function wants to do as I approach from the right or as I approach from the left? Where does the function want to go? In this particular case, you can try to plug in numbers. You can kind of see from the graph, the idea of this graph. It doesn't want to go anywhere. The closer you zoom in, the more times it oscillates between 1 and -1. So just when you think it wants to go to 1, boom, it switches direction and goes to -1. Just as you think it wants to go to -1, back to 1 it goes. This function is so erratic near the origin that we would say this limit does not exist. And we abbreviate that with D any. Okay, so you can only have one limit. There's only one number if it exists. If you're kind of not making up your mind between 1 and -1, that's a big hard stop. That's a no. Okay, so this function doesn't exist. So even though we have ideas of limits and where the function wants to go, there are functions out there, lots and lots of them, where the function just doesn't make up its mind, and we'll just say those limits do not exist. Okay, so this is sort of the scary one. This is the one that we have it is out there, but then we quickly throw it on the rug so we don't scare you guys. So let's go back to the land of nice functions and just do 2 examples where functions sort of behave the way we want them to. And I'm just going to do, I'm going to let you guys play this for a second. So let's say, what's the limit as x goes to 0 of the constant function 5? Let's just play around with this for a second. So think about this for a second. Let's get used to taking limits. This is a nice function. It's one of the nicest functions. How do you have a function that's nicer than a constant function? If I have 5 on the map, what's the line of the function f of x equals 5? Straight line. So as I approach 0, where does the function want to go? We all agree this is 5? Okay, doesn't that feel much better? You can sort of breathe easier. It's nice sound relief. So 5. Let's do another one. That's not as scary. I'm going to bring everyone back down. We'll come back to the scary ones later. Let's get back to happier places. Go to your happy limit. How about this one? X squared minus 4. I think this one's easy enough that we can draw a graph. This is the parabola pulled down 4. Y equals x squared minus 4. And I want to know what's going on at 4, which is going to be out here somewhere, whatever. Where does the function want to go? Now, I purposely drew this so that you don't see the graph, but hopefully you don't need to realize that this function, there isn't too much going on. It's a nice continuous function. It behaves the same as if you were just to evaluate it. So we actually extended the graph out here and drew it. This would become 4 squared minus 4. And the notion is that's 16 minus 4, which is, of course, 12. Now, this just happens to be equal to f of 4, and that's okay. So in the nice cases, where the function works, where the function you can evaluate, you can. And up here, by the way, this happens to be equal to like f of 0, if your function is the constant function. So this is sort of our very simple approach, our naive approach to limits that's going to work only in the very beginning, as long as we stay sort of sheltered from the complicated ones. But here's the first way to find limits. So you can check, you can find limits, by plugging in. Now, plugging in when possible, let's put it that way, because as we saw before, especially if we're working around 0, it doesn't always work. You can't always plug in. So if I'm looking at 0 and there's a fraction of the denominator, I can't do it. But if I have something like x squared minus 4, life is good, simple. All right, and we can do that. So some of the easier ones, just to start off with, there'll be no difference between limits and evaluating, but that'll go away pretty quickly. So start off somewhere, and again, have a graphing calculator handy as you do it. All right, good job. See you next time. All right, everyone, in this video, we are going to make a function that finds the local extreme, the local max and mins of a function. I'm going to assume